Balancing chemical equations. Balancing of a chemical equation may be defined as the method of making the number of atoms of different elements on both the sides of the equation equal. The balancing of chemical equation can be done with the help of hit and trial method. In this method, the coefficients before the symbols or formulae of the reactants and products are adjusted in such a way that the total number of atoms of each element on both the sides of the arrowhead becomes equal. This balancing is also known as mass balancing because if the atoms of elements on both sides are equal, then their masses will also be equal. Let us discuss the major steps involved in balancing a chemical equation. 1. Write the chemical equation in the form of a word equation. Keep the reactants on left side and the products on right side. Separate them by an arrow pointing from reactants towards the products. 2. Convert the word equation into a symbol equation by writing the symbols and formulae of all the reactants and products. 3. Make the atoms of different elements on both sides of the equation equal by a suitable method. This is known as balancing of equation. Do not change the formulae of the substances while balancing the equation. Let us illustrate the balancing of chemical equations with the help of an example. 1. Zinc reacts with dilute sulfuric acid to give zinc sulfate and hydrogen. Solution. The word equation for the reaction is zinc plus sulfuric acid gives zinc sulfate plus hydrogen. The symbol equation for the same reaction is zinc reacts with sulfuric acid to give zinc sulfate and hydrogen. Count the number of atoms of all the elements on the reactant side and then the number of atoms of all the elements on the product side, that is, on both the sides of the equation. As the number of atoms of all the elements involved in the reactants and products are equal, the equation is already balanced. Let us have a look at another example. The word equation for the reaction is magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen. Let us try to find the solution. The symbol equation for the same reaction is Mg reacts with HCl to give MgCl2 plus H2. The balancing of the equation is done through the following few steps. Step 1. Count the number of atoms of all the elements in the reactants and then of products, that is, on both the sides of the equation. You can see that the number of magnesium atoms are equal to 1 on both the sides. At the same time, the number of chlorine and hydrogen atoms is not equal. Step 2. It is always convenient to start with the compound that contains the maximum number of atoms, whether of reactants or of products. Then use appropriate coefficients to balance its atoms. In this case, the compound is magnesium chloride. Here, the magnesium atoms are already balanced on both sides. To balance the atoms of chlorine, put coefficient 2 before HCl on the reactant side. The equation may be written as Mg reacts with 2HCl to give MgCl2 plus hydrogen. Step 3. Now check the number of atoms of different elements on both the sides of the equation. These are equal. This means that the equation is balanced. Let us take another example. Iron reacts with water to form ferric oxide, liberating hydrogen gas. And now the solution. The word equation for the reaction is iron reacts with water to give ferric oxide plus hydrogen. The symbol equation for the same reaction is iron Fe plus H2O gives Fe2O3 plus H2. The balancing of the equation is done in the following steps. Step 1. We count the number of atoms of all the elements in the reactants and products on both the sides of the equation. A look at equation reveals that the number of hydrogen atoms are equal on both the sides. At the same time, the number of iron and oxygen atoms are not equal. Step 2. On inspection, the number of oxygen atoms in the reactant, that is water, is 1, while in the product ferric oxide, these are 3. To balance these atoms, put coefficient 3 before H2O on the reactant side. The partially balanced equation may be written as Fe plus 3H2O gives Fe2O3 plus H2. Step 3. In order to equate hydrogen atoms, put coefficient 3 before H2 on the product side. As a result, the hydrogen atoms on both sides of the equation become 6 and thus are balanced. The partially balanced equation may now be written as Fe plus 3H2O gives Fe2O3 plus 3H2. Step 4. In order to balance the iron atoms, put coefficient 2 before Fe on the reactant side. The equation formed may be written as 2Fe plus 3H2O gives Fe2O3 plus 3H2. Step 5. On final inspection, the number of atoms of all the elements on both sides of the equation are equal. Therefore, the equation is balanced. We will now discuss another example. Methane burns in oxygen to form carbon dioxide and water. Here is the solution. The word equation for the reaction is methane plus oxygen gives carbon dioxide plus water. The symbol equation for the same reaction is CH4 plus O2 gives CO2 plus H2O. Following are the steps to balance the equation. Step 1. Let us count the number of atoms of all the elements in the reactants and the products on both sides of the equation. Number of carbon atoms are equal, that is 1 on both sides. At the same time, the number of hydrogen and oxygen atoms is not equal. Step 2. The number of hydrogen atoms in the reactant CH4 is 4, while in the product water these are 2. To balance the hydrogen atoms, put coefficient 2 before H2O on the product side. The partially balanced equation may be written as CH4 reacts with O2 to give CO2 plus 2H2O. Step 3. Further, number of oxygen atoms in the product is 4, while these are 2 in the reactant side. In order to equate oxygen atoms, put coefficient 2 before oxygen on the reactant side. The equation may be written as CH4 reacts with 2O2 to give CO2 plus 2H2O. Step 4. On final inspection, number of atoms of all the elements on both the sides of the equation are equal. Therefore, the equation is balanced. Writing symbols of physical states. The physical states are also mentioned with the help of specific symbols known as state symbols. S for solid state, L for liquid state, G for gaseous state, AQ for aqueous state. Na in solid state reacts with 2H2O in liquid state to give 2NaOH in aqueous state plus hydrogen in gaseous state or H2 with an up arrow. This equation shows sodium is in solid state, water is in liquid state, sodium hydroxide is in aqueous state, and hydrogen is in gaseous state. Up arrow reveals that gas is liberated. CaOH whole twice in liquid state reacts with carbon dioxide in gaseous state to give CaCO3 with a down arrow and H2O in liquid state. The state symbols are of utmost significance for those chemical reactions which are accompanied by evolution or absorption of heat. They can be exothermic or endothermic. 2H2 in gaseous state reacts with oxygen in gaseous state to give 2H2O in liquid state along with 572 kilojoules of energy. This is an exothermic reaction in which heat is evolved. N2 in gaseous state reacts with oxygen in gaseous state to give 2NO in gaseous state, absorbing 180 kilojoules of energy. This is an endothermic reaction in which heat is absorbed. In some chemical reactions, conditions of temperature, pressure, catalyst, etc. are mentioned either above or below the arrowhead that separate the reactants from the products. Gaseous nitrogen reacts with gaseous hydrogen in the presence of iron catalyst at 500 degrees centigrade and 200 atmospheric pressure to form ammonia in gaseous state. Carbon dioxide in gaseous state reacts with water in the liquid state in the presence of sunlight and chlorophyll to form carbohydrate in aqueous state and oxygen in gaseous state. Certain chemical reactions proceed in both directions. The reactants change into products in forward reaction. The products are converted into reactants in the backward reaction. In the forward reaction, nitrogen reacts with hydrogen to form ammonia. In the backward reaction, ammonia splits up to form nitrogen and hydrogen. Such reactions are called reversible reactions. Let us revise. Information conveyed by a chemical reaction. A chemical reaction tells about reactants and products participating in the reaction. A chemical reaction informs us about the symbols and formulae of all substances involved in the reaction. It tells us about the atoms and molecules of the reactants and products that are involved in the reaction. It gives us information about the weights of the reactants consumed and of the products formed in the reaction. It tells us about number of gram atoms or gram moles of the substance that are participating in the reaction. In few cases, it tells us about the physical states of the reactants and the products, and also about the heat evolved or absorbed during the reaction. A chemical equation does not tell us about the feasibility of a chemical reaction. Example: copper reacts with sulfuric acid to give copper sulfate and hydrogen. This reaction seems to be feasible but does not take place. We cannot get any clue about the rate of reaction from a chemical equation. This means that it does not tell us whether the reaction is slow or fast.